Okay. Thank you. So I hope the microphone is working. Yeah. Yes. Hello, everyone. I hope you are still awake. Yes. So is it okay? Yeah, I would like to shift a bit the perspective.
Pull it closer to you.
Closer?
Yeah. Otherwise, you'll speak down into it, which makes it difficult. So pull it off your throat and then speak up.
Wait a second. Okay, good. So I would like to shift a bit the focus from the to modeling forest responses to environmental change. So shift the focus a bit more from the observations to the modeling. And when Tom invited me for this meeting here, he asked me to talk about what needs to be done to really improve our understanding of global forests and how they are changing. Super difficult. And a perspective on this from the modeling side with any angle you like. Super easy. I can talk for 2 hours, so please stop me after 15 minutes. So when I talk about modeling here, I talk about process-based models. And these models basically simulate vegetation and soil organic matter. So basically the processes in above and below ground related to carbon, water, and nutrients, and how they respond to climate, land use, atmospheric CO2 concentration, and deposition and changes in these drivers. So this is the input for our models. And then the models basically simulate processes related to primary production and growth, plant biogeography, soil biogeochemistry, and population dynamics and disturbance. So they are all like in these black boxes, a lot of equations and formulations. And as you can see in the red arrows, they are all interrelated. So it's big models and they simulate the processes. So for my talk, I thought it could be interesting to go a bit more into detail into the question about how long does carbon remain in forest biomass and put a bit a global perspective on this from the modeling side. So we can look into the mean turnover time of live biomass, which is given here as tau, so which is basically the mean time that the carbon remains in living vegetation in years. And that we can take the output from our model on simulated stock of carbon in live biomass, here given as the C wedge, over the carbon turnover flux, so here given as the F turn, which is the total loss flux of live biomass. So that is simulated by our models. And then we have a nice study that was led by Tom, where we run several vegetation models or process-based models, which you can see here in the upper 6 panels. So these, in these panels here. So these are 6 process models that were run with similar input data and conditions. And what you see in these maps is the carbon residence time, the mean for 1985 to 2014. And if you just look at the colors, which indicate the carbon residence time, in blue is short carbon residence time, in yellow, orange is long carbon residence time, you can see that they are more or less all over the place. So there's no agreement among the models. And you can also see that we have calculated like a satellite-based carbon residence time map, and also the models do not very well agree with this map. So to give you a bit of numbers, so if we look at the global mean value, the global mean carbon residence time, there the models range between 11 to 22 years, which is relatively close to the satellite-based estimate of 19 years. But of course, the regional variations, if we look into these, they are much more pronounced. So we have here a range from 10 to 25 years in the Amazon forest that is simulated by the models, and 5 to 30 years in boreal forests. So what we can conclude from this figure is that there's no consistent picture from the models. So To understand a bit better why we see these differences, I thought it would be interesting to look a bit more into this carbon turnover flux, this F-turn, which is the total loss flux of live biomass, which is basically the sum of different fluxes related to mortality. So F mort here, the carbon turnover flux due to plant mortality or woody carbon loss. Then fluxes related to leaf and fine root senescence, and fluxes related to reproductive processes. So these are all the losses that are simulated. And now what you can see here is how this is represented by the models. So what you basically see is how much each of these turnover processes contributes to the total turnover flux. And you also see here again that the fraction of these turnover processes varies strongly among the models. And you can see that in some models, this turnover flux is totally dominated by mortality, while in other models, it's more evenly distributed to these different processes or fluxes. So to put some numbers on that, so in the models, the processes related to mortality are responsible for 37 to 81% of this turnover flux, which is quite a large spread or variation among the models. So to summarize this, we can see here that there's a large uncertainty about the importance of these processes related to carbon turnover fluxes. So what I mean with importance is the importance that is given in model development to represent these processes in the models. But also the problem is often that these processes are not very well constrained, so that it's super difficult to put them into models if we don't know how it really works. So how can you put an equation or a formula on something that you don't know? And then, of course, the next super important question is then how will these processes or carbon losses change in the future? That is even more complicated. So I thought we could have a more detailed look into the mortality processes. So how will forest mortality change in the future and how is this represented by the models? So what you can see here in this figure is, first of all, that there are different mortality processes that are represented in the model. So it's 5 processes. It is listed here as in the legend. So we have mortality related to disturbance, related to vitality, some background mortality, heat stress mortality, and some other mortality processes. And the second thing that you can see here in this figure is that all these models account for different combinations of these mortality processes. So it's not that all the models have the same mortality processes represented. And the third thing is that you can see in this figure is that they also strongly differ in how they simulate then these changes in mortality into the future. So on the x-axis, you here see simulations that are run from the year 2000 to 2100. And you can see that there are very different projections about mortality rates in the future. So that is what we have. So the question is what needs to be done to respond to Tom's question. So on one hand, I think it's super important to improve these mortality-related processes and the process understanding in order to be able to implement this in some way into the models. And this can be done, to my opinion, by ecosystem experiments and large-scale or long-term observations. And I think here is these ecosystem experiments, something like drought experiments, are really super important to really get into the physiological processes. And also why I think that ecosystem experiments are super important is that this carbon turnover time integrates over a wide variety of processes. So it's not only about mortality, it's also about other processes like carbon allocation, reproductive processes, below ground carbon that in the forest can dynamically change. So the understanding of the interplay of these processes is super crucial. And therefore, I think something like ecosystem experiments are super important, especially for model development. But of course, also long-term observations and remote sensing data can help here. So in the second part of my talk, I would now like to show you a little bit what we have done in order to improve the model that we are working with. So we're trying to include a more process-based representation of forest mortality, and there we were focusing on including the effects of drought in our dynamic vegetation model. And the basic assumption of this whole implementation is that there is a pressure gradient between the soil and the leaf water potential, and that this is the driving force for the water flow through the plant. So we include different hydraulic strategies, as you can see here. So we have a soil water potential, and if this soil water potential is decreasing, so the axis here is reversed, then we have some strategies that keep their leaf water potential constant, and we have some strategies that follow this soil water potential. So we can simulate these different hydraulic strategies, as we call them. And then we implement also the hydraulic failure and drought mortality into LPJ-GES, which is the process-based vegetation model that we are working with in my group. And we do that by combining the leaf water potential, the soil water potential, and calculating a xylem water potential. And then we look into the percentage loss of conductivity in the xylem, and we calculate a probability of mortality based on empirical data that we got from the literature. And what we can do then with this new implementation of this drought mortality, we can, for example, simulate the drought impacts of the very strong 2005 drought in the Amazon region. So what you can see here on the top left map is how strong this drought was. So this is a drought indicator, a deviation from the mean climatological water deficit. And you can see that this drought was very strong in the central and western part of the Amazon basin. And the observed losses that we got from inventory plots that Oliver was talking about this morning was estimated to be 1.6 petagrams of carbon. And what you can see here now in these two lower panels are the simulations with our process-based model, LPJ-GES. And you can see on the left side, the standard version of the model, which just basically simulates some random mortality events. And on the right side, you can see now the new implementation of drought mortality in the model. And you can see that we can much better represent now these potential carbon losses from drought in our model. And we get much closer to the observed values of carbon losses with our new implementation. And what we can then also do is that we can try to simulate the observed trends in the carbon sink that Oliver showed this morning. So we have here from the inventory plots the estimates about the net carbon sink, the carbon gains that are still increasing, and the carbon losses that are increasing stronger, so that this is leading to a decline in the carbon sink in the Amazon region. And if we now run our models, we can more or less reproduce this trend, which is not the case with other dynamic vegetation models. They cannot reproduce this decline in the carbon sink, and they can also not simulate this increase in mortality. And therefore, we hypothesize that these drought events, these repeated drought events, are a major driver for these carbon losses, as Oliver already mentioned this morning. So to conclude from this exercise is that it's super important to use the available data from ground-based measurements to inform and test models, and to develop also new model formulations and test those. And that we can also use the models the other way around to provide hypotheses based on our model simulations to guide experimental work. So in this case, we can now put a quantitative hypothesis on the effects of repeated strong drought events about the decline of the Amazon carbon sink. Is there still time?
Short.
Okay, I will just quickly say something about, so these carbon losses, these fluxes of carbon loss can also be related to management processes such as harvest. So we also have included, which is more important for the European scale simulations, we have included detailed management options in our model. And at the European scale, if we want to see how climate change or management activities affect carbon storage, for example, in forests, we of course have to reproduce the age structure and species composition. And once we have this, we can do super interesting analysis about possible management options where we can use our model to not only look into carbon, but also into other ecosystem services and try to provide potential management options to balance all these ecosystem services in a balanced manner. So that was very quick. I'm happy to talk about this more with you in the coffee break. So what I think what would be important is to include also in these models a more detailed representation of human impacts on forests to, for example, plan for sustainable sustainable management of forests. And then, of course, yeah, there are many ongoing developments in the whole modeling community. So what is super important is really to account for climate feedback. So couple these models to regional climate models to see also what the effects on local climate are, detailed land and forest management, implementing phosphorus cycling, which is super important for the tropics, but also nutrient cycling in general, and to also improve the representation of impacts of extreme events in these models. So now I will stop and thank you for your attention.
Thank you so much, Anja. That was super interesting. And then, yeah, we can get Cornelius back here. I don't know how it works with the online speaker, if she can. Okay, great. So we get her also